All right, so moving into building statistical simulations with Python and Pandas, specifically in Numpy. This is going to be how we proceed forward. So I'm going to share my screen here, and we'll get going. Okay, so before the break, I built out a descriptive statistics in Pandas notebook. So I want to make sure that you'll have access to this. So here's what I'm going to do. I'm going to make a new GitHub repository, as we do. I'm going to make this in the Code Up classroom so that you'll have access to it easily. Statistics. Exercises. Okay. Set this to public to make sure that this is public so you'll have access. And then I'm going to create the brand new repo. Okay. So I have an empty repo on GitHub, and what I care about most of all is this clone address here. So I'm going to grab that clone address and head to my terminal. And on my terminal, I have my easily folder, and inside of here, that's every other repository exists in here. So I'm going to do a git clone and then paste the name of that new repository. I get a heads up, you appear to have cloned an empty repo. That's fine. I did that on purpose. And so we see that I have easily statistics exercises. So because so much of the classes already has easily prepended, I'm going to change the name. Just call it statistics exercises. Like that. And then what I can do is then move that descriptive statistics notebook that I did earlier and put it in the stats exercises. And then we can change directories into stats exercises, right? We'll be sure to add, commit, and push. Actually, I just need to push. Because I clone this, I don't have to worry about setting up the origin or anything else. So my cloning is so nice. Okay. So I'm going to fire up a new notebook here and build out a little bit of a structure for us. Okay. So I'm going to make a new Python notebook. And this will be simulations intro. Import Numpy and import Pandas. And the first thing I want to set us up for success here with is how to run a simulation with Python, Numpy, Pandas. It's only a couple of steps. Step one is we figure out a way to represent our data. Step two, we create a matrix of random data where the number of rows is equal to the simulations and the columns is equal to the trials. So for example, rolling 2 dice 10,000 times means rows is 10,000 and columns equals 2 because we roll 2 dice each time. Right? If you're only rolling 1 die, you only have 1 column, right? I'll be demonstrating concrete examples of this very, very shortly. So we apply our aggregate function row-wise to get the results of the simulation. And then finally, we apply a final aggregate to get our probability. And when I say aggregate, think of whatever we're looking for, mean, median, min, max, right? Okay, we're totally going to start out with some dice rolling and some coin flipping, stuff like that, and then work our way into more complicated and more realistic and real world setups. For the first setup here is an example. Let's see. Start, close it out, leave. Okay, cool. So we're moving into this simulation module, and we're going to rely both on Pandas and on Numpy together. Okay. And if you see this, if you're trying to follow along with the curriculum line by line, if you see this example that says import viz, the viz library, the code for that is linked over on the overview note on visualizations in case you're trying to do like replicate the curriculum. I'm going to be doing without the visuals. I'll be getting fairly close to that. So there's a couple of tools that we'll be using with Numpy, because Numpy has a very rich random library for randomness. And here are some, not all, but here are some of our selections. We can use np.random.choice, and choice, we can feed in a list, and this list can be of numbers. This list can be a list of strings. And we can also provide in the weighting or the probabilities. Uniform generates a uniform distribution, go figure. And we can set in different parameters as the arguments to the function. And random on its own, this kind of throws folks for a loop sometimes, that so many different programming languages generate random numbers between 0 and 1, right? So generating like integers, we would have to do rand int, for example. Rand n generates random numbers with a standard normal distribution. That's a fancy way of saying that bell curve, just standard normal distribution. A lot of things are distributed that way, like height, weight. A lot of things in the physical world, right, are follow a normal distribution, or standard normal distribution. And we can do np.random.normal, and we can specify the mean and the standard deviation specifically, and this will give us random numbers that match that distribution. Okay, so I'm going to set us up for success here by following my own recommendation. Let's build out an example problem. This will be fairly trivial. You've probably done or seen something like this a whole bunch of times. But my attitude here is, let's answer questions experimentally rather than theoretically. We'll get into the theory after we have a good horse sense of what the data is like, right? And really the theoretical, anything having to do with theoretical probabilities, that's just approaching if we could run an experiment an infinite amount of times, right? So let's do something super simple. What's the probability of flipping heads on a coin? Well, we know theoretically already that that's 50% chance of getting heads, 50% chance of getting tails, because that's probably the easy part of the theoretical probability. But let's try to answer this actually experimentally. And how many experiments do we want to run? Let's run a whole lot of experiments. Let's flip a coin 100,000 times. Figure out the probability of getting heads. Ability of flipping heads. Okay, so the first thing that I'm going to do to represent our data is I will make kind of like a list of outcomes. Like what are the two possible outcomes, or what are all of the outcomes? So let's find a way to represent our data. And with heads or tails, we can do heads and tails. It's at this stage in the game, if we had some other state of things, we could add that other state in here, right? So far, we're just working with a list of strings, right? We'll say number of trials. So our number of trials, we agreed that that'll be 100,000. Or I just kind of picked that out of a hat. We didn't agree on it, but a nice high number, not like 7, right? And what we can do here is let's actually flip our coins. So we'll do flips. We'll hold np.random.choice and see how the choice is making it's hitting that list of strings that holds the outcomes. And then with the size argument here, I'm going to say that the size is the number of trials, which is 100,000. So we will randomly choose. Now choice is, because there's 2 outcomes here, choice is going to give an even probability to each of these unless we make it an unfair coin on purpose. So let's take a look at what these flips look like. We have tails, tails, heads, some more heads, some tails, right? So far, so good, folks. We've done step 1. We're representing all the possible outcomes. It's only heads or tails, like the probability that a bird snatches the coin, a raven grabs the coin and flies off. That's not part of my outcomes here. It's just heads or tails. We flip the coin 100,000 times. And check this out. We know that we want to sum up the number of heads, and we want to get a ratio of the number of heads to the entire data set. That sounds like an average to me. So we can do how many of the flips match to be the string heads. Do y'all remember our good friend double equals when we're running with Numpy or Pandas series? Numpy array or Pandas series, we get back an array of Booleans, right? Tails is not heads, which is why it's false. The second index, tails, is not heads, which is why it's false. Heads is heads, which is why it's true. Now here's the cool thing about Booleans or arrays of Booleans in Numpy or Pandas is the trues count as 1, the falses count as 0, and we can do things like get the average number of heads in this data set. So our experimental probability after flipping 100,000 coins, our experimental probability of flipping heads is it's not completely correct, right? We know theoretically that that's 50%, but it's darn close, right? That's rounding errors away. And what if we only flipped 10 coins? We would have a lot more error if we flipped 10 coins, right? What if we flip 100 coins? Well, we start getting closer. What if we flip 10,000 coins? We get even closer. And we can run this multiple times, right? The number is changing because we're actually generating random choices each time, right? So having a nice high 10,000, maybe 100,000. If you crank this up into the millions and millions, NumPy's fast, but you're going to be cranking away a lot of processing, right? We could do it though. We could pull up a million. That was pretty quick, right? So like every probability book that's like, okay, now pretend that you've flipped 1,000,000 coins. Well, we don't have to pretend. We just did it. What we can't have here, though, sadly, is we can't have an infinite number of flips. Because Python won't work that way. Right? We could run an infinite loop, but then we couldn't get anything out of it. Right? Cool. So we figured out a way of representing our data. So step one, we listed our outcomes. Step two, we created a matrix of the random data, which was pretty easy because we were only flipping one coin, right? And then once we had our array of Booleans, the matching, then we applied an aggregate function to that, the mean, to get the average. Okay. All right. Would y'all like to see another example of this process? Cool. Let's do another example. I'm going to try and build up on the complexity little by little. So in this other example, let's start with our same process. So let's build out our problem. What is the probability of rolling a 5 on a 6-sided die? So what are our outcomes here? Our outcomes here are 1, 2, 3, 4, 5, and 6 pips on the die. Those are our list of outcomes. So step 1, represent our data's outcomes. Step 2, and you don't have to name your variables what I'm naming them, but I'm partial to this, right? So we're starting with the outcomes and trials here. I'm just going to abbreviate that. We'll do this 10,000 times. And then let's get a bunch of rolls here. So step 2 is create the data. So our rolls will be np.random.choice. So we're randomly choosing from that list of outcomes. The size is the number of trials. Okay. And then if we take a look at our rolls here, we have all kinds of rolls, right? So we can set up, if our problem is what is the probability, maybe an even easier way of putting it, what are the chances we roll a 5? So our chances become which of the rolls equal 5 and how many of those rolls on average show up as having 5. And this should be somewhere around 1/6 because we know theoretically 1/6 is the percentage chance that you'll get any given pip to show up on a die, right? And there's variants of this problem, right? Variants of this same problem. What is the probability? We'll roll a 5 or a 6 on a die, on a 6-sided die. Well, we might know what that is theoretically, but we can say rolls that are greater than or equal to 5 top mean. We can say what is the probability of rolling less than a 3, but not including 3. Well, that's rolls less than 3. And then we apply our aggregate. How are we doing, folks? I'm trying to avoid all of those like purple marbles and green marbles kind of probabilities questions. What we're trying to do here is just get after the actual answer of performing lots of trials rather than relying on any theory at this point, right?
So if we wanted to find like the probability of rolling anything but a 3, we just do like rolls doesn't equal 3, correct?
Yeah.
Okay.
It's almost as if you can take your English, and if you know your pandas well enough and your Python well enough, we can say rolls that don't equal 3 get the mean. And theoretically, that's 5 out of 6. Experimentally, though, we're able to answer this question pretty quickly, right? And we can kick this around pretty nicely. Yeah.
Is there a way to convert that to a fraction? Maybe I missed. Or is that not something that usually happens then?
To my knowledge, Python doesn't have fractions as a data type. There
Gotcha.
are some languages that have fractions as a data type. There might be some tricks you can use to do that, but
okay, cool.
Yeah. Good question. Awesome. Let's see. I see something in. Okay. All right. So we're doing fairly straightforward stuff. Flipping a coin, rolling one die a whole bunch of times. Are y'all ready to add another layer of complexity here? Just another layer to the lasagna. Let's roll 2 dice at once. Oh my gosh, we're adding the complexity to the problem, right? So let's do this. Our steps are still the same. Step 1, figure out a way to represent the data. Step 2, create a matrix of random data, right? Where rows is the simulations, and then columns is the trials. And then we'll apply an aggregate row-wise to get the result of each simulation. And I think after this example, this will make a little more sense. And then finally, apply a final aggregate, probably dot mean, to get our probability. Okay, so looking at this one, let's set up a problem. What are the odds of rolling snake eyes on 2 dice? So we don't have to worry about the theoretical sense or anything like that. Let's, in fact, this approach to doing statistical simulations has a name, a very special name. You may have heard of it before. We were doing simulations like this. This is called the Monte Carlo method, named after a quite famous, named after Monte Carlo, right? Quite old and quite famous gambling, right? So in setting this up, let's set our outcomes here. Our outcomes are going to be 1, 2, 3, 4, 5, and 6 pips. We're not rolling any funky dice, just 6-sided die. And so step 1, represent our outcomes. Step 2 is create a matrix of random data. Rows is the simulations, and columns is the trials. And I want to make a distinction between simulations and trials, and I'll be able to do this now. So let's say we want to, I made a typo up here. I shouldn't have said trials there. I should have said simulations. I made a typo. I called these trials up here, and these should be simulations. Simulations. Cool. These are not trials, but and simulations and simulations. Okay, cool, because there's a difference between a simulation and a trial. So simulation is the number of times we run the experiment. Trials is the number of things in each experiment. right? Forgive me for mislabeling that earlier. So our number of simulations, let's run a million dice. Why not? And then our trials will set this up. So let's do some rolls. And our rolls will be np.random.choice, and we'll choose from our outcomes. And then on what we can do here, the size argument can set our simulation and trial size. So if we're rolling 2 dice at a time, our trial is 2, because we have 2 dice per each experiment. We're running a million experiments though, right? And so we'll say n trials 2, because we're rolling 2 dice with each experiment. So we have our outcomes, and then we can actually set a size here, and the size will be a tuple, and we can put the number of simulations first, and then the number of trials second. And this produces a whole big mess of rolls. So this is kind of wild. In the first roll, we rolled a 6 and a 6. The second roll, the second experiment, we rolled a 4 and a 6. The third experiment, we rolled a 1 and a 1. Now, as I'm looking at this one, I'm realizing if the only possible way we could sum, like what's an aggregate row-wise, that we could produce snake eyes is if we have a row that sums to 2, right? So step 3 is apply an aggregate row-wise. Now, we didn't have to apply an aggregate row-wise when we were only doing one thing, but now we're rolling 2 dice, right? Apply an aggregate row-wise. So let's do this. We will do our rolls, and we will sum along axis 1. So let's roll this out. So axis equals 1 means sum across the rows. So see how the 6 plus the roll of 2 6s sums to 12. The roll of 4 and 10 sums to 10. The roll of snake eyes, which is what we're after, sums to 2. Right, so now we can call these sum of each sum of rolls, right? I'll print this out on the screen and ask for questions at this point. How are we doing on this step 3 here? So far, so good. There's a couple of ways of setting this one up. I'll show a different approach to this problem in just a little bit.
Ryan, is it always going to be axis equals 1?
If axis equals 1 means row-wise, and axis, so what if I did a sum axis equals 0? I wouldn't, with axis 0, I'm not summing by the rows, I'm summing by the columns. So I should get 2 different numbers. See how I summed up all of the rolls of the blue, like a blue die, and then all of the rolls of a red die there. So axis equals 0 means columns, and axis is 1 is rows.
Gotcha, thank you.
Mm-hmm. That's a good question. I'll put this in a comment, and I'll say axis equals 0 means sum up the entire column. So if we have, so this is doing a different a different thing entirely. Rather than adding each roll, this is adding all of the rolls from one die and then adding all of the rolls for another die. Yeah, and axis 0 is a default. Absolutely. Absolutely. Thank you, Ravinder. Cool. All right, so that's, now that we have our sum of rolls, what we can do is say the sum. So now we can move on to step 4, apply a final aggregate, right? So step 4 is the sum of rolls that equal 2, which means the only rolls that are snake eyes, let's get the average amount of time that they show up. And that's 0.027. So we're saying add up all the times that an experiment and a simulation of the same thing. The trials is the number of things in each experiment. Add up all the times that an experiment produces the sum of 2. Okay. And so theoretically, we know that rolling a 1 on a 6-sided die is 1 out of 6. And if we have this twice in a row, this should be, these two numbers should be pretty close. All right, so we can say, we can print out our theoretical probability of rolling snake eyes is, which is (1/6) times 1/6. And I need to put my calculation in. So 0.27 repeating, 0.27 and some change. Not too shabby. Not too shabby. So I am bringing out the theoretical probability here, just to try to connect us back to something you may have seen before, or at least some logic that you've approached before. Cool. Questions on this last one? I added a layer of complexity because now we're rolling 2 dice at a time, right? So I'll open up for questions right now about this last one. I mean, take a moment to think about what we've demonstrated so far, how you're doing, where you feel you think you've got it, but maybe not 100% sure about.
This may be covering further down the line, but if you want to find the sum that comes up the most often, like which one has the most possible combinations, like is with 2 dice, like if you roll a 7 or if you roll a 9, which sum, starting top to bottom, can you like list out the probabilities of which one would show up the greatest amount of time?
Now you're doing probability distribution. That's our next, actually.
Okay.
That's
Yeah,
what we're gonna do.
We can simulate this, right? Yeah, it's it's dovetailing into the next lesson, right? But we can look at that question through what we're up to already. So what is the probability of rolling a 7 on 2 dice? Right, there could be a number of ways of producing this. We could produce this with 1 and 6, 2 and 5, 3 and 4, 4 and 3, right, 5 and 2, and 6 and 1, as an example. So we can set this up. So step 1, represent our outcomes. Outcomes is 1, 2, 3, 4, 5, and 6 pips. Step 2, generate a matrix of random outcomes. Simulations is the rows, and then trials is the columns. So we can do this. So let's see. Get my handy dandy NumPy here, and we'll say roles np.random.choice. We will be choosing from the outcomes. I don't have to worry about the making this unfair, because we want a fair probability on all of these. And let's do simulations is, let's do, our size will be 10,000 simulations. And how many dice are we rolling each time? 2. 2 dice per. So we can say size is equal to simulations, and then size is equal to experiments and number of dice per experiment. Okay. So what we can do is we can do the same logic here. Step 3, apply a row-wise aggregate. It doesn't have to be sum, but that's what we're going to do here because it helps us answer the question. So sum of roles, this will be roles dot sum, and axis equals 1. Again, axis equals 1 to apply sum to rows. Okay, and then let's take a look at our sum of roles. We'll just put these out. Okay, so we get a bunch of different numbers. So what we can do now is say the number of sum of roles that matches 7. Let's count up the number of times that occurs and get that as a proportion of everything. And we see that about 17% of the time, we can expect to roll some form of 7 on our die, on our 2 dice. And this is where I think I'm not even going to go into the theoretical probability, because to do the theoretical probability, we'd have to do a little bit more work here, right? And I'm not going to set this up algebraically or anything else. I'm just going to do the trials. Right.
Could we do that like as a list with like 1 through 7, and it would list out each probability?
Yeah, I think I see where you're going.
Yeah.
What are our possible outcomes of rolling 2 dice? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, right? These are all of the possible outcomes that the sum could be, right? Possible sums, or possible sums. And we could do Is this what you're getting at, David?
Yes.
Cool. The answer is yes, right? And then we can say y is why is the sum of rolls that match the number dot mean is in a list comprehension for n in sum of- will this work for me? Yeah. Hey, look at that. Now we don't, at this layer of abstraction, I don't know what all these outcomes are, or I don't know what the constituents were here because we've lost the original dice rolls at this point, right? But if we look at, let's look at the sum of rolls. Let's look at the first 10 of these or so. And then we can look at the first, same with the probability. So we can see the probability of rolling a 4 on 2 dice was 8%. The probability of rolling a 7 was 17.21%. That's what we saw here too. Is this what you were asking about, David?
I guess what I was, if we could find a way to like put into almost like a table, and we have our values 2 through 12, and then in the column next to it be like you'd have a 2.7% chance for rolling snake eyes and 13% chance for 5 or whatever it may be.
Yeah,
I guess that was like the ultimate. What I was trying to see if we could make that.
The short answer is yes, we can. It will help us a lot to get into the next lesson, though, to fully answer your question, in my opinion.
Cool.
You can do it. You can do it with this stuff. It's a little too much. It would be one of the more challenging questions if this was an exercise question. We can do it. Yeah. For right now, though, we are coming on lunchtime, right? Lunchtime. Handy dandy lunchtime. So I'm going to add, commit, and push my work here, and be sure to take a lunch. We will come back at 1:32, and we'll pick up with a little bit more. Pick up with a little bit more. Great engagement, y'all. See y'all after lunch.